Hello everyone, my name is Josh Humberston and I'm coming from the University of New Hampshire where I work with Dr. Thomas Lippman. I'm also working with the Army Corps of Engineers Field Research Facility, which has been sort of the premier federal level coastal research facility for decades now. And down there I'm working with Dr. Jesse McNinch. I want to acknowledge them both right up front because they've been huge and instrumental to this work I'm going to be talking about. And that work I'm talking about is getting a better grasp of and understanding our coasts as they are right now, and then starting to predict their futures a little bit better than we're able to. And so the first question we have to ask ourselves is, why do we care so much about our coasts? Well, they're truly one of our most valuable natural resources. Two examples shown here is the state of New Jersey brings in over 98 million visitors most years, and that contributes to over 500,000 jobs and over $44 billion in revenue. Another example on the West Coast is the city of San Diego, a coastal city of nearly 1.5 million people, known for its beautiful beaches as well as its iconic deep harbor, which hosts one of the largest US naval bases in the United States. Already 50% of our population lives within just 50 miles of the coast. That's expected to increase by 10% in the next 10 years alone. And so what exactly is the problem? We have these large, valuable land areas. Turns out they're very susceptible to the forces of nature. And a prime example is what's going on right now down in the Gulf as we see Hurricane Harvey devastate the Corpus Christi all the way up through the Texas coastline of the Gulf. Here's an example from Superstorm Sandy, which devastated a lot of the eastern seaboard. And you can see on the top the Outer Banks all the way down to Atlantic City in New Jersey. I'm going to be talking a little bit more about the Outer Banks because we're going to use that as our study area for this work. And the Outer Banks is composed of a lot of different barrier islands and shoal systems. And it extends for hundreds of kilometers along the North Carolina coast. At some points, the island system's over 5 kilometers wide. At other points, it's no more than 200 meters. And here's a very different view of the Outer Banks system. This is Hurricane Isabella passing over the Outer Banks, which devastated much of the island system. I'm going to show, here's a few pictures of some of that devastation from Hurricane Isabel and others. In the top right, your top right, you can see a whole new inlet was broken through the island system, obviously devastating the roadway as any other infrastructure in that area. You can also see in the bottom center an entire block of houses that was washed away by typical storm waves over the period of just 20 years. Taking another look at some of the Outer Banks, on the upper left and bottom right, you have Oregon Inlet, which is the only hydraulic connection between the ocean and Back Bay area for over 100 kilometers. And it's incredibly dynamic. You have sand shifting every single day. You can also see just how thin this island system can be, where at times you have a beach, a road, and then the Back Bay, and that's about it. So it's very vulnerable. Already the Department of Transportation in North Carolina has a lot of projects going on to compensate for these issues. They're building a new bridge over Oregon Inlet responsible for the recent power outage. They're also looking at an area at the Pea Island study area where a new inlet was broken through by a storm and then naturally reclosed. And they're also working on a Rodanthe jug handle, which diverts the main road out into the bay and then reconnects to the mainland. All these projects together are going to cost over $500 million. And so the big questions with all this in mind that we have to address is, one, how can we get a better grasp of the current state of these coastal systems? And then how can we start to predict the future evolution of them when they're so very large, complicated, dynamic, and so energetic, especially during storm events, that it's hard to make typical survey measurements. So it's these problems that I'm working with the Army Corps of Engineers at their field research facility on the Outer Banks to answer. And the approach we're taking is to develop some new observational technologies and methodologies to get a better grasp on this current state, and I'll talk about that in a minute. And the second approach is to use numerical modeling to provide context for those observations, and then use it to predict into the future what this likely state will be. So again, here's the Outer Banks from a satellite view on the left. Our study area is most of the northern half within this red square, and the elevation of that area is shown in this map on the right. The field research facility I'm working with is on the northern end, and we have 2 sub-study sites within that area. One is an open beach face, representative of much of the Outer Banks area, and that's at the Black Pelican site. And we have a second study site at Oregon Inlet. It's a very dynamic inlet system. Flipped to the left here, so that north is essentially to the left, you can see the two study sites. And the idea is that these two study sites, or these two different environments, are often studied in isolation because by themselves they're already large, complicated systems. So it's hard to get a grasp of any one in particular. But our approach is different. We're trying to look at these systems together and how they interact. As one evolves, the other necessarily co-evolves because there's a hydrodynamic connection between them as well as sediment transport pathways. So looking at Site 1 is our open beach face. And the idea is that what you're seeing here is a satellite view, and there's this large white strip going out from the coast. And this is actually a wave breaking pattern over a large bar feature that naturally formed. We see these features repetitively along the coastline, but we don't have a good grasp on how they impact the erosional susceptibility of the adjoining coastline or sediment transport along the coast, which either feeds to down current areas being accreted or being eroded. And just a short, easy model, not to scale, is on the bottom right of these bar features, and you can see how they begin to overlap. We do know that sediment is dominantly transported from north to south, as shown by this arrow. However, again, with these bar features, we don't know, are they sort of wobbling back and forth, allowing sediment to bypass? Or the other hypothesis a lot of people had is that they're sort of sliding along the shore as these coherent features. And it turns out it's very difficult to measure something of this scale because there's not always waves, there's not always satellite imagery available because of clouds. The second study site, Oregon Inlet, is a large dynamic inlet system, and what you're seeing is waves breaking on the ocean side. The typical model suggests sand is transported around the ebb tidal delta, this shallow area on the ocean side, slowly. We already know this is much more complicated in reality. Instead, we have sand being transported from the upcurrent island into the main channel. We know this because the Army Corps of Engineers dredges this inlet constantly, every single day, all year round, just to make it navigable for even small boats. Some of that sediment remains in the channel, some is washed into the back bay, but at least some of it is washed back out to the ocean side where it then interacts with waves. Waves then slowly push the sediment back towards the coast with tidal forces fighting against it. And so in a zigzag-like motion, we get sand transferred to this downward island. So the way that we're using a new way to study these sorts of systems is this radar inlet observation system, termed RIOS, which was largely developed by Jesse McNinch at the Army Corps of Engineers. It's sort of a typical marine X-band radar system that we've tweaked for our purposes, and it's run by this trailer which actually has solar panels as well as a highly efficient diesel generator, so it can run for months at a time collecting hourly measurements. And the type of data that we get from RIOS looks like this. So what you're seeing is the return from actual wave crest and the faces of waves that cause higher intensity returns from the radar system. This alone is neat, and there's a lot of military applications to this. For instance, Jesse's been working on a new system called Swift that you can mount to a smaller boat. It could run a transect along the beach and get a quick sense for some shallow versus deep areas of the coastline and where you might want to be approaching the shore if you're a landing party. I'm going to continue to be talking about the large-scale coastal systems, but I'd be happy to take any questions later about these military aspects as well. So we developed a lot of our methodology down at St. Augustine Inlet in Florida, and I'm going to play this video. And what you're seeing is 9 months of data of this system developing, and you can see sand shifting around. You might even be able to see sort of in the main channel, there's some bar features migrating from the inlet out towards the ocean. And we believe this is truly one of the dominant forms of sediment transport in the inlet system. So we took what we learned here and we started to quantify it using a time stack approach. So based on an offshore wave buoy, which is over 200 kilometers away, we predicted how much sediment we expected to be moving in this area. And that's shown in the bottom graph by the red line. We then use our RIOS data to show how much the actual bed forms on the bottom were moving. And that's shown by the black line. And you can see there's a remarkably good agreement for a system, or for predicting a system from 200 kilometers away from a single buoy. RIOS was recently collected from a 9-month deployment at Oregon Inlet and is planned to be deployed to the open beach face site at the Black Pelican site this fall. and we'll get the same kind of data at both of these locations. As I mentioned, the second approach we're taking is numerical modeling, and we're using the Delft 3D modeling suite, which is an incredibly powerful modeling suite developed in the Netherlands, where they're very worried about the effects of sea level rise on their country's coast. It can model tides, waves, sediment transport, and we're using a nested grid approach, which has a large coarse grid and then a more refined grid in our area of interest, which is the inlet and the open beach face. And that's shown here again. So if we look at this site, here's the refined grid area, and I'm going to zoom in on the Oregon Inlet part of this experiment, just to show you that in red, here's our coarse grid, and then we have this more refined grid around our area of interest, but still we have a lot of grid nodes, and we usually have 8 to 10 vertical layers as well. And knowing how complicated hydrodynamics are and fluid dynamics, and then adding on top of that the sediment transport aspect, it's incredibly computationally intensive. So when I tried to run this model on my computer at home, it told me it would take 9 years. My advisor wasn't happy with that, so we started scaling up, and now we're running it on the Exceed supercomputer network, where a model like this will take 2, 3, 4 days, something in that range, which is a lot more useful. Very quickly, I'm going to show some early results from this work. And this looks a little complicated. What you're seeing is very quickly tides flowing into and out of this inlet system. And you start to see some of the colors change, where it's getting darker, where it's predicting sediments being eroded, so it's getting deeper, and where it's lighter, you're seeing sediment accrete, and so it's piling up. So while we have a lot of fine tuning to do to our model yet, this is definitely going to be helpful to predicting how we can expect these systems to change over time. Another way to look at this is to look at the total transport. So in this map, zoomed in on the inlet again, you can see that it is indeed predicting sediment is transported from that northern island into the channel and then being washed out by the tidal currents as we predicted. So far, preliminary work suggests that RIOS is an excellent tool for looking at this large-scale, long time frame morphological change of our coasts. It also suggests numerical modeling is a prime tool to pair with this observations to start to predict, to get a more comprehensive picture and predict likely future states. We're continuing this work, putting a lot more sensors in the water to help constrain our model to reality and validate it. That way we can get a better sense of how well it's working and then start to run it months and even years into the future to understand how this whole island system is going to evolve. I wanted to round this whole talk out with a quick description of the moving the Cape Hatteras Lighthouse, the largest lighthouse in the United States. From 1870 to 1999, it was built about a kilometer away from the coastline. However, due to erosion, in 1999, it was perilously close to being knocked out by the next large wave event. And so what was considered a largely symbolic move by the National Park Service, they moved this lighthouse 2,700 feet back away from the coastline. And the idea is that if we're better able to predict how these systems are going to evolve, we can have a planned, orderly, more cost-effective retreat from these coastlines, rather than dealing with the repercussions as they happen, which is much more expensive, and we also don't want to try to continue fighting the forces of nature. We have enough enemies as it is. So I want to thank you for the federal sources, as well as the University of New Hampshire and a few individuals who have been critical to this work. And thank you all for being here. It's a great event.